To put a single kilogram of payload into low Earth orbit, you have to burn an enormous amount of chemical propellant just to fight Earth's gravity well. This mass fraction penalty means most of a rocket's weight is fuel, not cargo. But launching that same kilogram from the moon requires a fraction of the energy. Popular media often pictures space mining as capturing a platinum-rich asteroid and towing it back to Earth. The logistics of deceleration and atmospheric re-entry make returning raw materials to terrestrial markets economically unviable. The actual objective of the space resource industry is in situ resource utilization, or ISRU. This requires extracting and using materials exactly where they are found. This creates mass leverage. Every kilogram of rocket propellant or structural steel manufactured off-world is a kilogram that doesn't need to be hauled up the gravity well. Mastering lunar extraction severs our reliance on Earth's supply chain. It is the strict mathematical path required to make permanent off-world settlement possible. The moon is the most immediate and logistically viable target for ISRU. While deep space asteroid capture remains pre-commercial, the lunar surface is 3 days away and rich in usable mass. This orthographic projection mosaic from the Clementine mission maps the heavily cratered terrain of the lunar South Pole. These permanently shadowed regions are the most critical geographic choke points in the inner solar system. Because sunlight never reaches the bottoms of these craters, they harbor massive deposits of frozen water. In the cislunar economy, water ice is the foundational currency. A closed-loop ecosystem relies on extracting 3 pillars from the local environment. First is propellant. Second is life support. And third is infrastructure. The processing architecture that controls these 3 pillars will dictate the terms of trade and logistics for the entire cislunar frontier. Extracting water ice from these coals relies on thermal mining. Heating the frozen lunar regolith causes the ice to sublimate directly into vapor, which is then captured in specialized coal traps. Once captured, this water is purified and fed through an electrolyzer. Applying an electrical current splits the water molecules into liquid hydrogen and liquid oxygen, the primary components of rocket propellant. Water ice is concentrated at the poles, but oxygen is abundant everywhere else. It is locked inside the iron-rich minerals and glasses that make up the standard lunar regolith. This graphic maps the hydrogen reduction of ilmenite. Exposing iron titanium oxide to hydrogen reduces the mineral into iron, titanium dioxide, and water. This water undergoes electrolysis, stripping away hydrogen and releasing pure oxygen for life support. A second, more direct pathway is molten regolith electrolysis, or MRE. This cutaway of an MRE cell shows lunar regolith melted into a liquid. An electrical current runs through it. Metals pool at the cathode, while oxygen bubbles up at the anode, yielding up to 37.5% pure oxygen. Aerospace engineers weigh exact operational trade-offs, the relative mechanical simplicity and lower yield of hydrogen reduction versus the high oxygen yield and extreme thermal complexity of MRE. Perfecting these specific electrochemical reductions is the absolute prerequisite for human survival off-world. They turn dead rock into breathable air and fuel. Beyond oxygen, the lunar surface is a source of raw aerospace metals. The highlands are rich in anorthosite, a calcium-rich plagioclase that is roughly 25% aluminum by mass. Refining this anorthosite into usable aluminum alloys requires intensive chemical processing, such as the subhalide method or high-temperature arc melting, separating the pure metal from silicon and iron. Long-term habitation demands biological sustainability through a closed-loop agricultural ecosystem. To grow crops, engineers target specific lunar deposits known as CREEP, which stands for potassium, rare earth elements, and phosphorus. These are heavily concentrated in regions like Oceanus Persilarum. In their raw oxide forms, these elements are not biologically useful. The material must be chemically processed into bioavailable forms, converting potassium into chlorides or nitrates, and extracting phosphoric acid. This refined CREEP material provides the critical off-world fertilizer required to sustain large-scale lunar hydroponics. Treating the moon simultaneously as a mine for industrial metals and a farm for CREEP transforms it from an expeditionary outpost into a self-sufficient logistical hub. Supplying a lunar base with pressurized habitats and replacement parts from Earth creates a severe logistical bottleneck. The solution is in-space manufacturing. The iron and aluminum extracted during molten regolith electrolysis and subhalide processing provide the raw feedstock. This electron beam melting printer fuses metal powder layer by layer in the moon's vacuum. It allows a lunar base to dynamically fabricate tools and pressure vessels. These space-built parts hold a structural advantage. They aren't over-engineered for Earth launches. Powering these industrial foundries and printers requires massive energy inputs, driving the parallel development of space-based solar power arrays. The closed loop of extract, process, and print scales infrastructure indefinitely. It transitions humanity's footprint from temporary outposts to heavy industrial settlement. The engineering schematics for ISRU are rapidly outpacing the international legal frameworks designed to govern them. The bedrock of space law is the 1967 Outer Space Treaty. Article 2 prohibits national appropriation by sovereignty. No nation can own a celestial body. The traditional interpretation held that space was the province of all mankind. For decades, this uncertainty over property rights stifled commercial investment. The passage of the U.S. Commercial Space Launch Competitiveness Act in 2015 introduced a new legal framework that prioritizes commercial interests over legacy international norms. The legislation clarified a critical legal distinction. While a nation cannot claim sovereign territory on the moon, a private citizen or corporation can own, transport, and sell the resources they extract from it. The United States formalized this interpretation multilaterally through the Artemis Accords. This framework establishes deconfliction protocols and safety zones to protect private mining operations. By legally decoupling territorial sovereignty from resource extraction, the U.S. created the regulatory certainty needed to attract institutional venture capital, starting a global race for space-based assets. While the U.S. strategy relies on a decentralized public-private commercial ecosystem, China operates on a highly centralized, state-directed industrial policy. This timeline outlines China's Earth-Moon Special Economic Zone, projected to generate $10 trillion annually. Targets include asteroid probes by 2034 and a lunar station by 2036. By 2049, China aims to lead space, mirroring their terrestrial rare earth dominance. The immediate geopolitical priority is securing first presence rights. The first nation to establish operational mines will dictate the de facto rules of behavior and set the safety perimeters. If a single nation monopolizes cislunar logistics, they secure immense strategic leverage, effectively controlling the refueling supply for all deep space operations. Ultimately, the victor of this geopolitical race will not be decided by treaties, but rather by applied engineering. It goes to whoever successfully scales molten regolith electrolysis and resource extraction first. Space mining has graduated from science fiction into hard metallurgy and international law. It is the immediate physical foundation of the next global economic order.